Okay, so we're in the process of proving the area formula. So let me remind you what that is. So you've got a mapping, a Lipschitz mapping from A into Rm, and this A is contained in Rn. And remember, the area formula is for the case when n is less than or equal to m. So you're mapping into a higher dimensional space. And this is Lipschitz. And A should be Hn measurable, or Ln measurable, same thing, is we're in Rn. And remember, Ln and Hn are the same in Rn. We have this, the area formula simply says that the integral over A of the Jacobian factor, integrated with respect to Lebesgue measure, is equal to the integral over all of Rm of the number of points in the pre-image with respect to n-dimensional Hausdorff measure. Remember, this is the same. Remember, this is empty when y is not in the image, so this is the same as saying the integral over Fa. Same thing, right? And you recall that we actually were fairly well advanced in the proof. We were looking at case 1. That was the case when f is differentiable at every point of A. Remember, Rademacher's theorem only says that it's differentiable at almost every point of A, but let's assume in case 1 that it's differentiable at every point x in A. And furthermore, that the rank of df x equals n. That's maximum rank. And you recall that we proved there that we showed we proved that you can actually decompose A into a countable union of measurable sets, not disjoint, but a countable union of measurable sets. Where Aij equals the set of X with some rather nice properties, namely that F, make a bit of space here because I want to play around with this a bit, set of points such that Fx, Fy minus Fx is less than or equal to 1 plus epsilon to the, let's get this exactly, 1 plus epsilon times what we call tau j, y minus x, and bigger than or equal to 1 minus epsilon times tau j, y minus x. For every y in the ball of radius 1 over I centered at the point x intersect A. And also another inequality that the Jacobian matrix, that's this thing, remember this Jacobian matrix is just the square root, this is Jacobian at a point x, it's just the square root of the determinant of dif at x dotted with dj f at x. And we were able to squeeze that in between, again, rather precisely squeeze it the way these values are squeezed, namely jfx is less than or equal to 1 plus epsilon times the determinant of torr j, and bigger than or equal to 1 minus epsilon times the determinant of torr j. And here torr j is a linear map. Each torr j is a linear map. So there's a whole sequence of these, j equals 1, 2, etc. So you've got a whole sequence of linear maps, and you define aij to be the set of points where these inequalities hold. Now, of course, that wouldn't be very helpful, except that we proved that A decomposes into a union of those sets, right? So you can decompose all of A. So every point of A is in one of these sets, at least, maybe more than one. So we get rather precise control of the difference in terms of these linear maps. That's the point. Somehow this is a linear approximation result. That's really what it is. Okay, and now we've just got to stare at this a little bit in order to see that it's actually giving us something rather good. Namely, well, this suggests, see, this requires that this only really works for points y as long as they're close enough to x, within a distance 1 over I of x. So that suggests that we should decompose each of these aij's into subsets of diameter less than 1 over I, so that we can apply these inequalities freely. So that's the next step in the proof. You simply so decompose. So choose sets bk, b1, b2, etc. pairwise disjoint. Remember, PWD is our abbreviation of pairwise disjoint. So choose b1, b2, etc. pairwise disjoint with each bk contained in one of these aij's. For some j, and with the diameter of bk less than 1 over I for every k. You can clearly do that. You can always break sets in Rn up into smaller sets and make them pairwise disjoint in the usual manner. So let's do that. We break it up. So then let's see, what does this tell us then? Well, that tells us in particular now that this is certainly true if you're in one of the sets bk. If both y and x are in the same set bk, then of course this is trivially satisfied, because by definition the diameter of bk is less than 1 over I. So every point in bk is less than 1 over I distance from every other point in bk. So one consequence of doing that breakup is that we can say that this is true for every xy, every pair of points in bk. We actually threw away a bit of information there, because we're only looking at points bk now in the same, in one of these particular sets of diameter less than 1 over I. So we get that. And this would be true, of course, for every x in bk, as long as bk is in aij. But that'll be true for some j. So we have that. Now we've just got to look carefully at this inequality. It says something extremely strong. We've just got to rewrite it in a nice way. That is that if instead of writing it this way, you write it as f, instead of fy, I can write it as f composite with torr j to the minus 1, composite torr j, looks sort of silly, right? I mean, it's the same thing, but it's written slightly differently. Minus, and the same thing here. I can rewrite this as f composite torr j to the minus 1, torr jx. So this middle term can be written like that. Now these outside terms can similarly, this is remember torr j is linear, so this is torr jx minus torr jy, so less than or equal to 1 plus epsilon times absolute times the distance tau j y minus tau j x. I can rewrite that way, and likewise this guy, 1 minus epsilon times tau j y minus tau j x. And that's for every x, y, and bk. Now, if you stare at that for a minute, you'll see that actually that says that this inequality, for example, is on this side, says that the Lipschitz constant, lip, of f composite tau j to the minus 1 restricted to bk, that is less than or equal to 1 plus epsilon. That's really good. And likewise, this side says the same thing about the inverse. This right side says that the Lipschitz constant of f composite tau to the minus 1 restricted to bk o to the minus 1, the inverse, is less than or equal to 1 over 1 minus epsilon. And that's, so both of these are very close to 1. Remember, epsilon's an arbitrary positive number. I should have emphasized that at the beginning. We're just letting epsilon be any positive number to begin with, and all of this discussion was related to that particular epsilon. So we have that. But remember, we've got a nice result about that. That tells us that, that means that, let's see, this is, restricted to bk. So that means that, oh yeah, sorry, that's, I didn't do that quite right, did I? These are not restricted to bk, they're restricted to tau j bk. That's wrong. So these are restricted to tau j of bk. Likewise, this is restricted to tau j of bk. So you just have to, so this is an example of something that looks like a sort of a mass at first, but then when you look at it in the right way, it suddenly says something extremely strong, and which we can then make use of. So remember, we've got a result that if lip f is less than or equal to L, say, remember one of our results is that then the n-dimensional measure of FA is less than or equal to L to the n times the n-dimensional measure of A. So let's apply that with A equals bk in our case, and let's apply it to this, instead of applying it to F, we apply it to this guy. Oh, sorry, again, same mistake. We're going to apply it with A equals tau j bk. So let's use this. So this tells us that the n-dimensional measure of fbk is less than or equal to the Lipschitz constant, which is less than or equal to 1 plus epsilon to the nth power times the n-dimensional Hausdorff measure of tau j bk. And likewise, this one tells us that the n-dimensional Hausdorff measure, we're applying it to the inverse, so we'll have an fbk on the right this time. So fbk is bigger than or equal to 1 over 1 minus epsilon to the n times hn tau bk, tau j bk. So actually we get something really strong out of that. So let's combine these. Let's combine this into one string of inequalities here. So in other words, we proved that hn of fbk is less than or equal to 1 plus epsilon to the n hn tau j bk, and it's bigger than or equal to 1 minus epsilon to the n hn tau j bk. Very nice. So that really turns out to be extremely powerful. So this, these things that didn't look so useful at first turned out to be extremely useful. And not only that, remember Tor J is just a linear map from Rn to Rn. And we can use one of the classical theorems about Lebesgue measure. You remember one of the classical theorems about Lebesgue measure is that the n-dimensional, remember these are, Hn is the same as Ln in Rn, so I can put Lebesgue measure there, same thing. Now remember, one of the classical theorems about Lebesgue measure is that the Lebesgue measure of a linear image is exactly equal to the determinant, the absolute value of the determinant, times the Lebesgue measure, let's still call it Hn, but it's really Lebesgue measure because we're in Rn, bk, like so. And likewise this side, same thing. This is the same as 1 minus epsilon to the n. This is the same as 1 minus epsilon to the n times absolute det Tor J times Hn of bk. Like so. So that's great because we're getting some real inequalities here. We've got the n-dimensional Hausdorff measure of the image less than this factor close to 1 times the determinant. Now remember that second inequality here tells us about that determinant. That's less than or equal to, it would have been nicer if I had have written this. I don't remember, did I write it this way last time or did I put a JF on each side here? I don't remember. Notice it's equivalent if I just change notation a little bit, just putting the inequalities this way. This is better for us. So det Tor J. That may involve a different choice of epsilon, but of course the same argument exactly applies. So for us this is better. So let's do it that way. So and then det Tor J is less than or equal to, so we get another 1 plus epsilon here. So that becomes 1 plus epsilon to the n plus 1 power, n plus 1, times the determinant determinant J, the Jacobian at x times Hn bk, and likewise on the other side, same thing. Bigger than or equal to 1 minus epsilon to the n plus 1 times the Jacobian of f at x times Hn bk. And that's true for every x in bk, for every x in bk. So in particular, that'll be less than or equal to, let's put it here, that'll be less than or equal to, well, this is true for every x, so that's certainly less than the average of f over this set bk. So this is less than or equal to 1 plus epsilon to the n plus 1 times the integral of j over bk, the integral over bk jfx dhn, because the integral is less than the maximum or the sup. So this is true for every x. So certainly the integral is less than or equal to the sup here. So I could put a sup here if I wanted to, sup over bk, since it's true for every x in bk. So I could put a sup over bk for that one, and I could put an inf over bk for this one. Inf over bk for that one. So you can replace that by the integral, because the, other way around. This should be sup, this should be inf. I can put either inf or sup, because it's true for every x, and this one should be sup, since we want the inequality to go the right way. So that inf is less than the integral. Well, inf times the measure is less than the integral. So we get 1 plus epsilon to the n plus 1 times this. So let's rewrite all of that. So the conclusion is that Hn of the image is less than or equal to 1 plus epsilon to the n plus 1 times the integral over bk of jfx Thn, and it's bigger than or equal to 1 minus epsilon to the n plus 1 times the integral over bk of j fx dhn. And that's true for every k. So now we simply sum over k. So sum over k. Well, then this gives us, remember, the union of the bk's. All the bk's are in aij, and the union of the bk's, we've broken up all of the aij, pairwise disjoint. Whoops, I don't think I said that. So we do break up the entire collection, the union over j. It's 1 to infinity. So each bk is in one of them, and we break up the entire union. So union over the k's of bk should be the same as the union over j of aij for every I. Doing this for each I. And the diameter, we were using this diameter less than 1 over I as well. So that means that when we sum over k, here we get integral over ai. Let's agree that ai is going to be this union over j. Notice we're holding I fixed here. aij, j equals 1 to infinity. So we get 1 minus epsilon to the n plus 1. Integral of the Jacobian, dhn, less than or equal. Now, what about this guy when we sum this? Well, keep in mind that by this inequality on this side, f is 1 to 1. F restricted to bk is a 1 to 1 function. So, if we take the indicator function, if we sum this over all possible, let's see, I want to take, right, so if we sum, oh yes, sorry, I want to say something about this. So I want to talk about that sum. Okay, so let's think about indicator functions again. Let's look at the sum of the indicator functions of these images of the bk's at a point y. K equals 1 to infinity. Well, f is 1 to 1, as I just said, on each of the bk's. So when you sum this, you get exactly the number of points in the preimage of y. In the set AI, intersect the union of the bk's. This is also, remember, the union of the bk's. K equals 1 to infinity bk, because the bk's break that up into a pairwise disjoint union. So this gives us exactly A0, the number of points. That's a nice general fact about indicator functions. If you've got some of the indicator functions of images, then normally that'll give you something that's less than or equal to this, of course, because some points may be covered more than once by this image, but here f is 1 to 1 on each of the sets. So when you take the sum of the indicator functions, you get exactly the counting measure of the entire inverse image of y. So now we just integrate this. So it'll give us this n-dimensional, the sum of this of these n-dimensional Hausdorff measures of the image of pk, sum over k, is equal to the integral of exactly this counting function. ai intersect f to the minus 1y dhny. dhny integrated over Rm. Okay, so let's transcribe that. So what we've actually achieved there is that 1 minus epsilon n plus 1, Hausdorff, the integral over ai of the Jacobian, dhn or dln, whatever you like, is less than or equal to the integral of over Rm of H0, the counting measure of AI intersect f to the minus 1y dHn is less than or equal to 1 plus epsilon to the n integral over AI of JF dHn. Okay, so that's that. And now one other point here. Remember, this is by construction, the AIs were the AIJs were increasing. Notice by construction, AIJ contains AI for every J, for every IJ by construction. So that means that the union of the AI union over J, J equals 1 to infinity, AI plus 1J contains the union J equals 1 to infinity of AIJ. So that means that this is an increasing sequence. That is, this says exactly that AI plus 1 contains AI. Okay, great. So that means we can use the monotone convergence theorem. So we simply take the limit as I tends to infinity. Everywhere here. The monotone convergence theorem, actually we use the monotone convergence theorem 3 times. We use it here, we use it here, we use it here. And that gives us exactly the inequality that we want, namely that integral over Rm H0A intersect f to the minus 1y dHn less than or equal to 1 plus epsilon to the n times integral over A JF dHn bigger than or equal to 1 minus epsilon to the n plus 1. It should be an n plus 1. So should it there, n plus 1. Integral over A JF dHn. So there we are. Now just let epsilon tend to 0 and you get this inequality. So it's a bit of a struggle and I had to go through that very quickly, so I'll leave it to you to really check out the details. You'll find all the details in the text. But in a way, it's quite a deep result, and it's under optimal conditions too, just using the fact that f is Lipschitz. So the proof is rather lengthy, but not that complicated. I mean, you're just somehow breaking things up in the right way. That does the thing. The main tool that we used there was this rather elementary inequality, a very elementary inequality. So the proof is lengthy and technical, but not really that many ideas involved in the proof. So, okay, so that takes care of case 1. Fortunately, the remaining cases are much easier. So this was the case when f was differentiable at every point and the rank was equal to n. The next, the case 2 is the case when f is differentiable at every point. So same thing, but this time the rank less than n. Remember, that means that then the Jacobian at x is equal to 0 for every x in A in this case. So this is the case when the Jacobian is 0. So that means this side of the identity that we're trying to prove is 0. Then we've got to check that this side is also 0 to show that the formula is correct. We have to show that the right side is also 0. Well, this is you don't have to really give a highly technical proof of this, fortunately. You don't have to repeat what we did in case 1 or anything like that. You basically just use a trick. And the trick is you define a new function, capital F of x, to be equal to f of x together with epsilon times x. So remember, this is mapping into Rm. So this is in Rm. and this bit's in Rn, so this whole thing is in Rm plus n. And so F is a mapping from A into Rm plus n. And notice the rank of F is certainly bigger than 1, right? Rank of F is certainly bigger than equal to n, right? And maximum it can be is n, of course. So rank of df. In fact, df, let's work it out. The ith partial derivative of capital F is equal to dif at x. And then epsilon, now when you take the ith partial derivative of this, you get the ith basis vector. So epsilon times ei, where ei is the ith basis vector. This is in the ith slot. So let's compute the Jacobian then of this new function, capital F. The Jacobian of the new function is you've got to take the square root of the determinant of this dotted with the ith partial derivative, that's difx epsilon ei, dotted with difx, dj rather, fx ej. Take the determinant of that, and that's just the determinant of epsilon ej. That's just the determinant of the matrix difx dotted with djfx plus epsilon squared delta ij. And of course that's positive, because this is a semi-positive definite matrix and this is a positive definite matrix, and we're taking the sum of the two, so that's certainly positive. So it's not equal to 0, and we can apply case 1 then. So case 1 applies. Now what does case 1 tell us? Well, notice that this function is 1-to-1 because of this bit here. This is a 1-to-1 function. So case 1 is rather simple. This, instead of this, is just either 1 or 0, depending on whether y is in the image or not. So this side of the identity is just the image, the n-dimensional measure of the image. And this side is equal to the Jacobian of this new function. Integral of the Jacobian of this new function, capital F dhnx. So now, let's stare at this for a minute. It is positive, but notice there's a general formula that you can check out, that's rather easy to check using the definition of determinant. If you take A plus epsilon I, where A is, let's call it M, where M is an n by n matrix, and I is the n by n identity matrix, you can check that that's exactly the same as det m plus an error term, and the error term is less than a constant times epsilon. Just check that out. Using the definition of determinant, you can see that that's the way it works out. So in our case, this means that this is equal to, let's read it off. This would be determinant of m, which is determinant of this bit, but that's 0 in this case, because the rank is less than n. So JF is 0. So that would be 0 plus something that's less than a constant times epsilon squared, even because we've got an epsilon squared rather than an epsilon there. So this is less than or equal to a constant times epsilon squared. So this is less than or equal to constant times epsilon squared times the n-dimensional measure of A. And now just let epsilon tend to 0. So Hn Fa. Oh, yeah, well, actually, we're not quite finished, though, are we? We've still got to check this. We're worried about this guy now, so what can we say about that? Okay, so Hn Fa is less than or equal to constant times epsilon squared. But on the other hand, this is bigger than or equal to, let's see now, what's the relation between capital F and little f? Well, you get back little f if you orthogonally project capital F into the first n coordinates, right? So let's call that P. So P is the projection that takes first, so we've got n plus m coordinates all together here on this side, and when we tell P, let P be the orthogonal projection into the first n of those. Then little f of x is exactly the orthogonal projection composite with capital F. So this is exactly equal to Hn of little fa is exactly equal to the n-dimensional Hausdorff measure of P of f of a. But now let's see, P, this is a Lipschitz projection, is a Lipschitz function with Lipschitz constant equal to 1. Flip of P is equal to 1. And we can use this general formula here for P instead of F. So HNP of any set, let's call it B, is less than or equal to Hn of B, because the Lipschitz constant is 1. So that means this is less than or equal to that. So now just to let epsilon tend to 0, and we see that Hn Fa is equal to 0. So that's it. So in case 2, you simply use this trick and directly use case 1 on this new function, and you just let epsilon tend to 0, and it gives you both sides. Both sides here are 0. So that's good. So that's case 2, and the only remaining case is when A is not differentiable at any point of A. That split off all the points where it's not differentiable, because we've taken care of all the points where A is differentiable here. So we've only got to worry about the set of points now where A is not differentiable. And by Rademacher's theorem, that's a set of measure 0. So case 3. So case 3 is the case when F is not differentiable. Not differentiable for every x in A. But then Rademacher tells us that in that case, Hn of A is equal to 0. And so there's nothing to prove then. Both sides here are 0, trivially. So that's the argument, and I had to do that fairly quickly, but you can read it for yourself, I'm sure, and it's an extremely important result. Okay, so we'll come back to the area formula later. It's one of the basic tools that we need in our later discussion. So now let me start our discussion of submanifolds. So let's give the definition first. So definition, M is an n-dimensional. Here, Q is going to be a number bigger than or equal to 1, an integer, bigger than or equal to 1. So Q is some positive integer. And M is an n-dimensional CQ submanifold, embedded submanifold. Of some higher dimensional Euclidean space. Say we're in Rn plus K. So the thing to keep in mind is that we've got some sort of smooth n-dimensional submanifold, and I want to give the precise definition of such an object. Okay, so M is an n-dimensional CQ embedded submanifold if for every x in M there exists a C1, a one-to-one CQ map C from some open set, so this is open in Rn, into some set W, which is open in Rn plus K. Open in Rn plus K. With X in the image of C, V, and that image this being equal to M intersect W. So the picture is something like this. Rn's down here. This is Rn plus K up here. And Rn's down here, and we've got some open set V down here. And we've got this mapping, C. And this is the image. So this is M intersect W. Let's write it down here. M intersect W. Set. Image. And X has got to be in here. In there. And this is C. And one other condition that's not quite clear initially why you need to impose this, but you definitely do, as I'll explain in just a second. The additional condition is that C to the minus 1 should be continuous. That's as a mapping from M intersect W back into V. So in other words, notice that guarantees that this mapping from V onto M intersect W is a homeomorphism. Thus, C V onto M intersect W is a homeomorphism, meaning a continuous in both directions. Okay, so that's the abstract definition of, oh, I forgot to say rank N, CQ rank N, it's important that it be maximum rank, CQ map, CQ rank N map. So it's rank N at each point. So get the Jacobian factored, so DC, which has got the matrix DICJ, where I runs from 1 to N. Now let's see. C is going from Rn up into Rn plus K, so there will be J components. C will have components C1 up to Cn plus K. So we want, that's an N by M matrix. J equals 1 up to N plus K. That should have rank M, rank N at each point, maximum rank at each point. So that's the definition of embedded C1 submanifold of Rn plus K. Now, the claim is that you can say more. Oh, I should first explain why you need this condition. That condition that the inverse should be continuous is to eliminate sort of weird examples like this when, for instance, in the case when n is equal to 1, we don't want to include cases that look like this, where m is a curve that comes around and almost meets itself, but not quite. See, that's not included. This is not a C1 submanifold because it's a smooth curve, yes, but you don't. But the inverse map taking you back to the interval. So this is a curve. It's really a map from an interval AB. Sure, and let's call it gamma. Gamma A starts out here and it ends up, though, getting almost, so this is an open set, an open interval. So it starts out here and sort of curls around and almost meets itself. We don't include that sort of case. It's also, this restriction is also to knock out examples like this, where you have something like the sine 1 over x curve together with that vertical line. That's not an example either. So you'll find a couple of examples discussed in the text that explain why you definitely need to make this hypothesis that the inverse map is continuous. Okay, so that's the definition, that you've got to be able to find such a mapping in the neighborhood of every point x. For every x in F. Must be able to do that. Now, there's a nice fact about c to the minus 1, and that is that actually c to the minus 1 extends to be a CQ function, not just a continuous function. So let's do that here. I claim that in a neighborhood of x0 of each point x0 in M intersect W, the inverse map c to the minus 1 extends to be a CQ function. And I want to explain why that is. So let's go back to this picture. So here's our map. Let's forget about the inverse for a minute. Here's our point x0, say. So there'll be some corresponding point in V that maps to that. Call it Z0. So x0 is equal to C0. And now this has got rank n. This matrix, this n by m matrix, or n by n plus k rather, matrix has got rank n at each point. So that means we can find n columns such that so there exists J1 bigger than or equal to 1, less than J2, less than Jn, less than or equal to n plus k, such that the determinant of di Cjl. So notice that here I is 1 to n, and j is also and l is also 1 to n. That's an n by n matrix. So that such that that is not equal to 0. That's the meaning of rank n, right? That you can find n linearly independent columns of the Jacobian matrix. So certainly there must exist J1 up to Jn. And let's agree to let pi be the projection. So I'm going to use a projection map pi, and pi is going to be simply the projection map that takes x1, xn plus k. Remember, this picture is in Rn, the top here is in Rn plus k. This down here is in Rn. So this is Rn down here. V is a subset of Rn, and we're up in Rn plus k. And pi is going to be the projection map that takes you onto those onto those coordinates with onto the J1 up to Jn components. So you simply take xj1 up to xjn. That's a point of Rn in Rn now. So that's mapping back down into Rn, same space as we started in here. So this is mapping down to Rn. So that's pi, and pi, notice that then pi composite C, well, that just picks out the J1 up to Jn coordinates of C. Jn coordinates of C. And we just got through saying that the determinant, so in other words, the determinant of d psi composite psi at the point, say, x0, at the point xi0, we're downstairs now, at that point xi0, that's not equal to 0. And pi composite, so this pi composite psi, see, psi is mapping up into Rn plus k, but psi composite psi is mapping in, leaving you in Rn. It's mapping Rn to Rn. So it maps like this. There's some image over here. Now, according to the inverse function theorem, since the determinant is non-zero at that point xi0, according to the inverse function theorem, there's a locally defined a CQ inverse for this function. So let's use that fact. So the inverse function theorem applies. There exists a neighborhood U0 contained in Rn, open, contained in Rn, such that, and a V0 contained in V, such that, in fact, let's even take a ball here. The inverse function theorem, of course, you can use one of these as a ball. Let's take a ball back here. So according to the inverse function theorem, there's a small ball centered here, radius rho, such that, this is the open ball, radius rho centered xi0, such that psi composite psi restricted to B rho 0, that open ball, is a CQ diffeomorphism. CQ diffeomorphism onto an open set, namely the set U0. So that means this picture, this is the ball, this is U0. And according to the inverse function theorem, if we let, let's call this C tilde, that's this restricted to this ball, B rho xi0 hat, that's going this way. According to the inverse function theorem, there's then a CQ inverse, C tilde to the minus 1. And so that, I guess we should take a break. So let's take a break for 5 minutes and we'll continue that discussion. I want to show you that that means that this map C, this map C to the minus 1 is actually a CQ map.
But I 没有，他下课弄的。
Then, so we're using the inverse function theorem here. Centered at the point xi 0. And this map C tilde that you get by just taking the J1 up to Jn components of the original map of the coordinate map C. And according to the inverse function theorem, there is this inverse that's also CQ going this way. Now, that actually, I claim that if you define, let's now define the following map. Define, so let's see, this is U0. So this cylinder that I've drawn here, that's intersecting the surface up here, this cylinder is pi to the minus 1 of U0. It's the set of points upstairs. It's an open set that project down onto this U0. And let's define phi. I'm going to define a map phi from this set. Let's call this U, so we don't have to use this rather clumsy notation. Let's call that U. It's an open subset of Rn. So this is open. It's this cylinder here, vertical cylinder. And let's define phi to be simply C tilde to the minus 1 composite with pi. Very simple map. And that's mapping. Let's see where it goes. It's a mapping on all of U. And then it projects pi down here into U0, and then C to the minus 1 takes you back into this ball, right? So this is a mapping from U back into the ball. Psi 0. The open ball's radius rho centered Psi 0. So that's nice. And I claim that that is, in fact, that actually matches the inverse. Let's check that. So let's look at C composite with phi. Notice that that is exactly the same as C tilde to the minus 1 composite phi, composite pi, composite C. But then C tilde is nothing but this thing, pi composite C. So this is pi composite C to the minus 1 composite pi composite C, which is the identity on U0. So C composite, the identity on the ball. This is defined on the ball. So this is the identity on the ball. P rho Psi 0. That's the identity map on P rho Psi 0. So indeed, phi restricted to that set up there, M intersect U, is indeed equal to C to the minus 1, restricted to M intersect U. So at least in some neighborhood of x0, namely in all of U as a matter of fact, C is an extension of C to the minus 1. So you can always get a CQ extension of these. When you're dealing with these local coordinate representations, these are called local coordinate representations. You've always got the nice property that actually the inverse, even though you assume initially that it's only continuous, the inverse does extend to this whole cylinder here in a whole open set containing the image point x0. It extends to a function that actually is CQ. Very nice fact. Okay, we'll make use of that in a little while. And let me make one more point about this nice picture here, about the projections. Notice that if you look at the thing, so we proved that phi composite C was equal to the identity on B rho, so it should also be a right inverse. So let's look at the C composite phi going that way. Well, let's look at pi composite that. That's equal to, again, phi. So what's phi? This is pi composite C, and then phi is exactly this thing again, pi composite C to the minus 1. Where are we? Phi, here it is here. C to the minus 1. So equals pi composite C to the minus 1. And that's the identity on U, 0. Oh, sorry. Let's see. I don't think I did that right. Let's just think about this thing. This is what's that supposed to work out? Yep. Okay, so so I shouldn't have done that. So so what I want to say here is that if you look at this map C to the minus 1 composed with C, that is a new coordinate representation. defined on this new set, U0. So let's call that capital C. So note, capital C equals C composite C tilde to the minus 1. That's a mapping from U0 up into U intersect M. Is a new coordinate representation. It's a new coordinate representation for M in the neighborhood of x0, near the point x0. Notice it still contains the point x0 by construction. And it's got the interesting property that it fixes the coordinates that we've labeled J1 up to Jn. So, and pi composite C. That picks out the J1 up to Jn coordinates of this function, right? Well, that's exactly pi composite C composite psi tilde to the minus 1, but that's exactly pi composite C composite pi composite C to the minus 1, which is the identity on U0 this time. The identity map on U0. On U0. So that means that this is sort of a distinguished this is a sort of a distinguished local coordinate representative because it has the property that it fixes. It doesn't move the coordinates labeled J1 up to Jn. It fixes them. So thus, let's just be definite. Suppose that J1 equals 1. This is really just a matter of notation, a matter of relabeling the coordinates. You can always do a relabeling map. If you want to use a permutation map, you can always arrange that you change the order of the coordinates using a permutation map. So suppose that you do that. And that means exactly that the first n coordinates that C fixes. It doesn't move them. It fixes the first n coordinates. So in other words, the map C has the property that it's defined down here in this set U0, and it has the property that it leaves the first n coordinates fixed. It just gives you back x. It doesn't move those. And then the remaining coordinates are exactly as defined. So they're this C n plus 1. The last k coordinates are C n plus 1 up to n plus k. And they depend on x2, of course, by definition. So in other words, you could sort of write this as x ux, which means it's the graph of a function, graph of a vector function. It's the graph of a function u, where the function u is just these guys. Ux equals c n plus 1 x. It's just the last k components of this new coordinate representation. So that's a very nice way of thinking about local coordinate representations. You can always make this computation, use the inverse function theorem together with this projection, and you cook up a new coordinate representation that basically means the manifold near the point x0 is just the graph of a CQ function. So we'll make use of that in various places. So that's rather important that you can view the any CQ submanifold you can view in that way. Okay, so now let's see tangent space. We want to talk about the tangent space of the submanifold. So let's redo our picture here. So down here we've got Rn, and we've got a local coordinate representation defined in some open set V. giving you an image up here, and this is M intersect W according to our definition here. So it's the image is M intersect an open set upstairs, and so we have that. And let's take any particular point X here. It'll be the image of some point xi from here. So X is equal to psi of xi. Now, I want to talk about the tangent space at X, which is actually independent of the local representation. So initially, you make the definition of tangent space. So the tangent space at the point X of M, so tangent space of M at the point X, by definition, means, well, to get tangent vectors, you simply take curves going through the point X. Let's call it gamma of t. So you consider a curve parametrized by a parameter t in some interval of the real line, and you want it to make sure it goes through the point X, and then the initial velocity of that at that point should be a tangent vector. So that's the definition. So the tangent space is the set of possible velocity vectors, initial velocity vectors. So it's the set of all those, such that gamma is a C1 curve. So it's defined on some little interval, and it's mapping into Rn plus k. And it's got to be at least C1 so that you can take derivatives. And it should be contained, the image should be contained in M, of course, otherwise it's not going to be necessarily tangent at the origin. So we want the image to be contained in M, and finally we want it to go through the point X at time 0, so gamma 0 X. So that's the definition of tangent space. In other words, the tangent space is simply the set of all velocity vectors, initial velocity vectors, of curves that are contained in M, whose image is contained in M, and which pass through the point X at time 0. Set of velocity vectors. Now, that's sort of the formal definition, and notice the definition doesn't directly depend on this local coordinate representation, but the problem with this definition is that it's not very convenient to use. So we would like to have a more convenient way of describing this, and that's the point. You can prove a lemma here that in actual fact, the tangent space is actually just the span of the partial derivatives of the local coordinate representation d1c at xi up to dnc at xi. Notice that makes sense because d1, that this is a vector in Rn plus k, because these are all vectors in Rn plus k, because C is mapping into Rn plus k. But it's not clear initially whether or not they should really be tangent. And that's clear, though, if you think about the definition here. So let's check that. So proof. Suppose you take any tangent vector. Well, by definition, that means that Tor is one of these initial velocity vectors. With gamma minus epsilon, epsilon contained in M, and gamma at 0 equals x. And then we can use this map that we cooked up here. Remember, we said that the inverse of the local coordinate representation near the point x can be written can be extended to be a C1 function. So, so use phi. We're using phi, but this time instead of in a neighborhood of this point x0, we're using it in a neighborhood of the point we're labeling x. In place of x0. And then observe that gamma of t can be written as phi of gamma of t times c, c composite c gamma of t, because because c maps from u intersect m down into u0, and then yes. Oh, wait a minute. No, that's not right. Phi. That's not correct, is it? It's not quite. Yeah, let's see. What's the point there? So, yeah, no, that's right, isn't it? C, we checked that, let's see. Phi is, yeah, C composite C, yeah. C, we checked that phi composite C was the identity on yeah. Did I do this right? Phi is mapping U to, yeah, phi is mapping U down to U0. And it's the, phi, C of phi, let's see.
It's potentially coupled with the
Yeah.
inverse.
Yeah, so that's right. So, but I still don't, I don't think I've quite got that right. This is nonsense, right? So,
You are correct, but I think it gets confused.
yeah, let's see. Yeah, okay, so phi is going from where to where? Oh, yeah. Phi is going back to here, right? Yeah, it's back to here, back to this. That's right, yeah, I am confused, right. So C first is pi and then composite with the invert. That was the definition of phi. So yeah, this is correct. This is actually that. So that's an identity for t small enough. Or t small enough. And that's good because these are composites of C1 functions. So we can just compute the derivative, gamma prime 0. By the chain rule here, these are nice C1 functions. So we can write sum j equals 1 up to n. Let's call this, let's rewrite this as C of sigma of t, where sigma of t is this. Sigma of t is phi of gamma of t. Okay, so that's a nice C1 curve. So this is, according to the chain rule, gamma prime is the jth partial of C, evaluated at sigma of 0, which is phi of 0, which is xi. Notice that phi of x0 gives you xi 0, or phi of x in this case gives you xi, and then multiplied by sigma j prime according to the chain rule. So that's what the chain rule gives you when you apply the chain rule to this composite function. And notice that that's a linear combination. That's in the span of these vectors d1c up to dnc. So that means that, that's the first point. So what have we proved? We proved that, that the tangent space of M is contained in the span d1c psi up to dnc psi. And we've got to prove the reverse inequality, but that's much easier because notice that if you take any linear combination, so you take arbitrary C1 up to Cn in the reals, and take any linear combination, take the linear combination with those C's, psi, that is exactly d dt, again by the chain rule, d dt evaluated at t equal to 0 of psi xi plus t times c, where c is the vector that you get by putting these constants together to give you a vector, c1 up to cn. So that's d dt at c equal to 0. And, but this, notice, is a curve. This is a curve that you could call gamma t, and it satisfies all these conditions. It's a map from, from an interval up into Rn plus k, whose image by definition is contained in M because C is a local coordinate representation, and gamma of 0 is equal to x, because when t is equal to 0 you get C xi, which is x. So indeed this is in Txm by definition. So the reverse inclusion is also true. So a span is contained also at xi, dnc xi, contained in Txm. So indeed, all the so the tangent space is much more conveniently written in this way. So it's just the span of these vectors, and in particular, each of these vectors themselves are in the tangent space. Each of these partial derivatives themselves are in the tangent space. Okay, so that's the tangent space. Now, we also need to talk a little about, we need to be able to do calculus or analysis on the manifold. So we do need to talk a little bit about things like directional derivatives and so forth on the submanifold. So let's do that. So let's start off with such an M, a CQ submanifold, n-dimensional submanifold. And let's suppose that we've got a Lipschitz function f defined now on M. So suppose f is M into some any dimensional space, it doesn't matter, into some Euclidean space, and this is n-dimensional submanifold embedded. And let's say it's at least C1. At least C1. We've been assuming CQ, but at least it's got to be C1 for what I'm about to say to make sense. And now let's define the directional derivative. The directional derivative of f in the direction tor at the point x is defined just as it is in Rn, except that we've got to be careful about this. We're on a curved space now, so we can't just take difference quotients the way we did in Euclidean space. So instead, let's use this characterization or this definition of the tangent space. So this is defined to be the derivative with respect to t equal to 0 of f of gamma of t, where gamma is one of these curves, where gamma is a C1 map on some interval of the origin into Rn plus k with image contained in M. Gamma 0 equals the given point. This is at the given point is x, so gamma 0 should be equal to x. And we want to talk about the directional derivative by the vector tor. So gamma primed 0 should be equal to tor. So here tor is in the tangent space by definition, because it's one of these vectors. And now you should be objecting to that definition because it appears that the definition depends on which curve you pick, right? So the first thing to do is to check that the definition is independent of the curve. So, so the claim is that indeed it is indeed independent of the curve, as long as you respect these conditions of the curve, choice of gamma. Let's check that. So suppose we've got another gamma tilde. Again, on some interval, this time on maybe a different interval, minus delta delta into Rn plus k, with the same conditions. Image should be contained in M, gamma 0 should be equal to x, and gamma prime 0 should be equal to tilde. And gamma tilde prime should be equal to tor. Now think about that. That means that, let's look at the quotient. Let's look at gamma t minus gamma tilde of t. Well, and in fact, let's look at the difference. Yeah, well, let's first look at that. Well, that can be written as gamma t minus gamma 0 minus gamma tilde t minus gamma tilde 0. And of course, by calculus, that's the integral from 0 to t of gamma prime s ds minus the integral from 0 to t of gamma tilde prime s ds. And that's equal to the integral from 0 to t of gamma primed s minus gamma tilde primed s. And if we take absolute values here, this is less than or equal to that ds. And notice this tends to 0. Both of these are tending to tor as these are C1 curves, so they're both tending to tor. So this tends to 0. In fact, even after you divide by t, 1 over t, we're supposed to be looking at difference quotients, so we take 1 over t, 1 over t, and that's less than or equal to the sup over s in the interval 0t. Or let's say it this way in case s is negative. So this is integral mod s less than or equal to mod t of absolute gamma primed s minus gamma tilde primed s. And of course that tends to 0 as t tends to 0, because both gamma primed s and gamma tilde primed s are tending to tor, same vector as s tends to 0. So that means that this quotient f, remember this is a difference quotient by calculus, so this is f t gamma t minus f gamma 0 over t. That quotient limit is clearly the same. So let's look at the difference. So this is the same as the limit. I can just add and subtract an f tilde, so it's same as gamma tilde t minus f gamma tilde 0. And the correction term is f gamma t minus f gamma tilde t, and all over t. And now this one is, by definition, giving you the derivative of this guy, and this one is tending to 0 by this statement here. So this tends to 0. So this bit tends to 0, so this limit is the same as that limit. So that's it. So it's independent of the choice of t. And there's one additional very convenient fact that you can also use here in the same sort of idea. You don't even need the curve gamma t to be contained in M, as long as you are careful about that. See, remember the Lipschitz extension theorem enables us to extend a Lipschitz function on the set M to the whole of the Euclidean space, right? So let f bar be any Lipschitz extension of f to all of Rn plus k, which we can do. Remember, f is just a vector. It's mapping into Rq, so it's got q components. And each of the components is a real-valued Lipschitz function. So you can use our extension theorem on each of the components of f. Remember that our extension theorem was for real-valued Lipschitz functions, but you can use that on each component of f, and that will give you a Lipschitz extension of the vector function. So let's call that f bar. And then observe that by a similar argument to this, you can make the following observation, namely that there's an alternative way of writing the directional derivative. Namely, the directional derivative, as long as tor is a tangent vector, as it is there, you can also write this as d dt of f bar of x plus t times tor. Now, notice that certainly requires checking, because this is a linear expression, so this is not necessarily in M. M is curves, and the x plus t tor goes in a straight line. But at least it's tangent to M at t equal to 0. So now let's check that that's correct. Simply define gamma tilde t is equal to x plus t tor. And then you'll see the same argument works here, but with f bar in place of f. So same argument that we use down here, here in particular, this argument, same argument implies that gamma t minus gamma tilde t over t tends to 0. By the way, I don't think I really quite finished the explanation of this. Notice we do need the Lipschitz property to check this is tending to 0, because we only checked the difference between the curves here. So I do need to make the point that the absolute value of this difference over t is less than or equal to the Lipschitz constant times gamma t minus gamma tilde of t over t. But that is tending to 0. So indeed, that's good. That works out. And the same argument works out here. So this implies, by the same reasoning, that f gamma of t minus f gamma tilde of t all over t tends to 0 as t tends to 0. So you can use this definition. Now, on the other hand, I've swept under the carpet a little bit one awkward point here. We don't know whether this exists or not, right? So what I've really proved here is that whenever this exists, whenever this derivative exists for some curve gamma, then it exists for all the other curves gamma too, and it also exists for this particular method as well. And you get the same answer either way. But it doesn't guarantee it exists, of course, right? So we really need to discuss that. Now, a fallacious argument for that would be to say, well, that's Rademacher's theorem. F is a given Lipschitz function, so it's differentiable almost everywhere, and that means all the directional derivatives exist almost everywhere. But of course, that's nonsense, isn't it? Because M is just a submanifold of Euclidean space of dimension n, and that's got measure 0 in the surrounding Euclidean space. So that Rademacher's theorem doesn't tell you anything. Because M is just a set of measure 0 if you're thinking about the surrounding Euclidean space. M is n-dimensional, and the surrounding Euclidean space is n plus k dimensional, right? So we need to talk about the existence. So what we've really proved here is that d tor f, if d tor f exists, then you can use any curve. It's independent of the curve. So I should have said that. So provided this exists, then it's independent of the curve and you can use any other curve as long as you respect these conditions in each case. And you can also use this idea as long as you use the Lipschitz extension. So that's good. You always get the, but that doesn't guarantee existence. So let's talk about that now. So existence. Of detour F. Okay, so let's think about that. So certainly we can apply Rademacher's theorem to the composite. That's Lipschitz, well, at least locally Lipschitz, is locally Lipschitz. I should actually explain why the just locally. You see, there's a general fact the composite of Lipschitz function is Lipschitz. No problem about that, of course. That's easy to check by definition, no problem. But is a C1 function Lipschitz? Well, not necessarily, because it could be defined on a rather nasty domain, like this, where this, it's an open set, but the boundaries could touch there. So C1 in general does not imply Lipschitz, because there's points arbitrarily close together here, but the dip function values could be quite a lot different at those points. So, but what is true on a convex domain, C1 implies Lipschitz. That is correct on any ball, for example. If you take a ball in here, then that's certainly correct. Let's check that. So suppose we have a C1 function on the ball. Let's call it C. Ball centered at some point xi, say. Then you can check Lipschitz, of course, because you can take f psi minus phi eta, and by calculus, that's the integral from 0 to 1 of the derivative of c at xi plus, I guess it's minus, xi plus t times xi minus eta dt. See? That's just calculus. Let's check that. At the top limit of integration, we have t equal to 1, and this becomes c eta minus p eta. That's correct. And at the lower limit, we have t equals 0. It's minus c xi, but there's a minus there, so that becomes plus. So that's correct. So that's correct. And now we can use the chain rule. This is integral from 0 to 1. Since it's a C1 function, this is the sum. Or just write it this way. By the chain rule, this is the same as xi minus eta dotted. I've still got the minus sign. Xi minus eta dotted with the it's xi j minus eta j summed from j equals 1 up to n. Xi j minus eta j times the jth partial derivative of psi at psi plus t times xi minus eta dt. And by Cauchy-Schwarz inequality, so let's take absolute values. Notice we definitely need convexity here. That's a convex combination. That's why you need convexity. So we're working in a ball. So eta's here, and the straight line joining xi to eta is still in the ball, right? So we really did need the convexity there. So now let's take absolute values here. And by Cauchy-Schwarz, this is less than or equal to the length of xi minus eta times the supremum of that, sup over the ball, p rho xi times mod d psi. And that's Lipschitz condition. This is a constant times length of x minus I. So indeed, C1 implies Lipschitz as long as you're either working in a ball or at least in a convex set anyway. But be careful, it's not true in general, unless you're really in a convex set. And so, F is at least locally Lipschitz. That means it's Lipschitz on any ball contained in the domain of the local coordinate representation. Now, the local coordinate representation is defined in this set V in Rn. So this is locally Lipschitz in V. So therefore, Rademacher applies. Rademacher implies that F composite C is differentiable almost everywhere. Ln almost everywhere in V. Because you can do this on any, you can use this local Lipschitz property on any ball and apply Rademacher on that ball, and you can do it anywhere for any subball. So therefore, it's true almost everywhere in the entire set V. If this is V in this case. So indeed, this is locally Lipschitz in V, and so you can use differentiability almost everywhere. Now, remember, one of the things we proved then was that this implies that for almost every xi in V, all the directional derivatives exist. Any place where it's differentiable, all the directional derivatives exist, and they give you a linear function of the vector involved. So in other words, for almost every xi in V, the following is true. All directional derivatives, d tor f composite C, exist and give you a linear function and are linear in tor. Notice that's what the differentiability condition gives you. It gives you not only the existence of all the directional derivatives, but it says that they're linear because the differentiability condition says that you've got a linear approximation to the function. So these are all linear. In other words, d of sum Cj tor j, j equals 1 up to n, for example, is the same of f at f composite C at psi is the same as the linear combination j equals 1 up to n Cj d tor j f composite C at psi. You can do that. So, so at least the composite function F composite with a local coordinate representation, all the directional derivatives of that exist. Now, fortunately, just think about that. That immediately says that all of these directional derivatives exist. Just let's check that. So, think about that. It's F of C xi plus t times tor ddt evaluated at t equal to 0. Well, what is that? That's exactly, so that exists, what we've just said is that that exists ln almost every xi in V, and it's linear in tor. Linear in tor. But you see, that's exactly, see, this is a curve. This is one of our gamma curves. It's a curve passing through xi at the point it's contained in M, of course, because this is a local coordinate representation for M. So in fact, we get this for free. This is exactly, by definition, this is d tor f at the image point phi xi, but that's d tor f at x, because psi xi is equal to x. That is, so in other words, for free you get that d tor at x exists for every Tor, and it's linear in Tor. And that's true for almost every xi in V. Now there's one slight catch, right? We want this to exist for almost every x rather than almost every xi downstairs. But remember, C is a locally Lipschitz function, and of course takes sets of measure 0 to sets of measure 0. In other words, if you have a set of measure 0 down here, you can just look at the part of that set of measure 0 in a ball. C is Lipschitz, so it takes that set of measure 0 up to a set of measure 0 there, using the general fact. Remember that lip of C of a set A is less than the n-dimensional measure of a set C of A is less than or equal to lip C to the nth power times the n-dimensional measure of A. So if A's got measure 0 down here, then the image also has measure 0 up there on the manifold. So magically we get this for free immediately. Just using Rademacher's theorem on the composite of F with a coordinate representation, you immediately deduce, without doing any extra work, that all the directional derivatives of F upstairs exist for almost every x, and they're linear in Tor. So we'll be able to make use of that fact. So at least maybe now we can start doing some analysis up on the manifold, and that's what we'll talk about next time. Did everyone get their assignment back? Okay. A couple of spares here.